So welcome back to System Software. We just finished up looking at the foundations of compilers, some basics of compilers. And before we get to our project, so the rest of the semester is going to be designing and building a back-end part of a compiler where we actually generate assembly code. Today I'm going to walk you through how your source code becomes a program and becomes a machine code program and a running program on your machine. I call this source to process. It's going to be a little free form. It's going to be mostly on the command line. I'm going to show you a lot of commands, but I'm going to show you each step of this process, each tool that's used, and what the input and output looks like in this long chain of language processing to actually get your C code, which there's no processor that runs it, into something that the system can run and is actually running resident in memory on your machine. But before I begin that, questions on the project. So today is this into post exercise that's due. It was just a hand copying exercise. Hopefully it was pretty straightforward. I didn't see too many questions about it. There was a few on the warnings versus errors. If you get a compiler error, it's not going to run. But the version of C++ and the libraries on USys was giving a warning, so I warned you. I sort of warned you ahead of time about the warnings. But any questions on that project? Any question on the proc project, which is due Wednesday? Questions from last time on any of the compiler stuff? I know the grammar stuff was a little onerous, but questions on any of this so far? Okay, let's go over homework 16. All right, so the question was to define a grammar for reverse Polish notation. So this was what it looks like. You have the it's postfix, the two operands plus the operator at the end. And the challenge was to create a grammar for this. Anybody have a grammar that they thought reflected reverse Polish notation? So we've already got terminals here in the language. Yeah.
It was basically the grammar that was in the lecture notes with the operators at the end.
Okay, so the grammar that was in the lecture notes, which was something like this, and you just swap the operand and the operator. So this grammar says you have some expression followed by another expression, because remember, reverse Polish notation can have nested expressions, followed by the operator. So if you said something like this, and then just use the same n, anybody have anything different or any other thoughts on this version of the reverse Polish notation grammar? Everybody got this? Okay. Do we need parentheses in reverse Polish notation? Why not? Yeah. Yeah, it's always evaluated according to the order of the operators. Yeah, so you don't need it. You can specify it explicitly. And if you think about this in terms of trees, this is just a post-order traversal of an expression tree. That's postfix notation. Infix notation, infix order. Of course, you need parentheses to make it clear the order. And then prefix notation, surprise, surprise, you can get from a prefix or a pre-order traversal of the tree. So if you recall how we modeled the syntactic structure of an expression using a tree, well, these different notations, infix, prefix, and postfix, are just different traversals of this tree. So post-order traversal gives you reverse Polish notation, postfix notation. And prefix gives you, pre-order traversal gives you prefix notation. All right, any questions on this? Questions on grammars? Questions on into post? So in the into post project, if you look while you're copying it, it's basically defining what we had talked about at the end of the last lecture, where we've got our grammar, which defines the syntax of the input language. And then we have computations, sometimes called semantic actions, that define what to do when you recognize this syntax in the input language. For the into post project, there was only 2 rules. If you enter a number, you just print out that number if you enter n. And if you are at the end, you exit an operation, this is the post order traversal part, then you print out the operator. And so this is a greatly simplified version of these actions here. So all of these operators are represented by one semantic action exit operation. N is just printing out. And instead of retaining a semantic value, we just print things out immediately. So these 2 semantic actions are effectively equivalent to these semantic actions, except instead of actually concatenating and saving the value, we just print everything out to standard out. So I know we haven't got, if you haven't seen C++ yet, there might be some new stuff here compared to C. I'll go over that next time when we go over the project. I'll just give you the C++ statements you need. Cout is what is like printf. So now cout is how you stream content to some open file. But I'll give you that next time. Who's seen C++? Who's done C++?
I use it in competitive programs.
Oh, okay. So, but in class, they don't do it in class here, right?
No.
Okay. So a few of you. But I'll go over all the things you need. Otherwise, you can use C. It's pretty much backwards compatible with C. So in these functions, and I'll give you all the functions. But we'll talk about it next time when I go over the compiler project. All right. Any questions on anything else? Yeah. It will be in C++. The project will be in C++. So yeah, if you are familiar with C++, by all means use C++. But the code you'll actually have to write will be, I don't think there's very much that is, it's in the intersection of C and C++, the stuff you're actually going to use. Yeah.
For most programming classes, they're like on the assignment, you can't use anything that we haven't learned in class. But if we're writing in C++ and we know like C++ stuff, can we just go like wild with that?
Yeah, if you want. Yeah, by all means. As long as it satisfies the specification of the project, program it however you like.
So I'm gonna find the most obscure syntax.
C++ is very easy to find that. It's a enormous language and getting larger. Yeah, so I'm not really much of a C++ programmer. Just know enough to do something, do this class. And I'm going to give you like a code template. I'm going to basically give you this listener class template, which if you did the reading, you'll know what a listener is. But I'll go over this again and when we go over the compilers. But you won't really need to know. You won't need to know C++ except for the very few number of constructs and statements I'm going to give you, and I'm going to give you examples of them. Okay. Any questions on the homework? Into post, the proc project, the processes project, compilers, basics of compilers. Yeah. I do have office hours after this. Yes, I'll have office hours after this for anyone who's having issues with into post. So I think there were some questions on EdSTEM. People were getting compilers. Just double check against the picture here. I know it's a little annoying with the picture, so the grader had pointed out that this looks like a 1, but it's an L in the font that I have. And he showed me where's the 1. There's a 1 in here somewhere. But yeah, there's a 1 here. So they're like in all fonts, lowercase l and 1 are quite similar. They're very similar. But hopefully through a little trial and error, you'll figure that out. But this is end L for end line, like /n. And this is argc, so it's a number, so this should be 1. Okay, let's take attention. Let me get into the main lecture. So today we're going to look at the nitty-gritty of how your C program actually becomes a process, actually becomes a running program. And I'm going to go into kind of show what I can show in the command line. Some stuff we can't see very easily, like in the kernel, but I'll show you each phase of the language processing steps. This is an overview of the many pieces of the language toolchain that produces your running program. And as you can see, it's not insubstantial. There's a lot of steps here. There's a lot of stuff going on under the hood. There's a huge amount of software and infrastructure that people have written for us over many decades to make your simple Hello World program just run on a machine and run on lots of different machines. So the code that you write looks very simple, but there's an enormous amount of infrastructure behind it that makes this possible. So let me just go through it as an overview, and then we'll actually dig into the code. And so this will be pretty freeform. I'm going to show you stuff on the command line. If you have questions, let me know. I know I've been trying to do better on tangents, but today is going to be a little more freeform. So if you want to investigate something more, let me know. I have specific parts of this that I'm going to go into more detail on, but I'm happy to go into more stuff if you have some curiosity. Okay, so we start with our C source program. This is like your Hello World program. And the first thing that gets run is the preprocessor. So somebody actually asked about this like a week and a half ago, and I resisted the urge to go off on a 2-hour tangent. But today I'll actually show what this looks like. So the preprocessor is actually something that runs technically before your compiler. This is what handles your pound include, pound define macros and things like that. And strictly speaking, it's not part of the C language itself. It's a part of the C ecosystem. But it's actually not part of C, and it creates lots of its own problems, which my lab does active research on, actually. All right, and then we get this preprocessed C. So this is C proper. This is the C language proper. And this is where the compiler comes in. I'm going to use GCC for this. But what's confusing about this is GCC actually runs these other steps for you. But strictly speaking, the compiler is just taking C code to assembly, or maybe machine code, but assembly for our purposes. And while the GCC C compiler suite will run all of these other parts of the language processing toolchain, the compiler itself is really just the translation from C code to machine code. And in this class, and in this diagram, that's assembly, which is another text format. Who learned about assembly? You learned about assembly in computer organization, right? I think everybody should learn this, right? And it's a text file that you write. And how does the text file become machine code? Because the machine just uses bits or like voltage signals, right? And so how do we actually get from text, because the assembly file is just ASCII text, which has numbers that are ASCII numbers. Those are not machine code numbers. How do we get to actual bits that the processor can work with? Well, that's what the assembler does. The assembler produces object code or machine code. Did you guys learn about this? Object files, assembly, machine code files? Okay. So the object files, this is an encoding of your machine code in binary, in the actual binary that the processor inputs. And now you might think, well, okay, we've got machine code. Why are we not done? Why can't we just run this on the processor? Well, if you had no operating system and you only wanted to run one program, you could. You could use this code to start running on your machine. But because we have this operating system, as we learned about, can manage processes for us, can manage memory, we need to wrap this in other code that the system will use to be able to load and launch this for us. And so and you may also have libraries that you depend on. So if you call printf, you didn't define printf anywhere in your code. This is another homework question. The .h file doesn't actually include the implementation of printf, as we'll see. And so where does that come from? Well, if you have multiple pieces of code that you want to combine, this is what the linker does. Did you guys learn about the linker in computer organization? Also no linker. Okay, so the linker takes multiple machine code object files and combines them together. So this is how you're able to have library code. So you call printf, but you didn't actually write printf. Somebody else wrote it. And it's the linker and the system that manages this library of existing code that you can use. It also helps create an executable file. It makes a file in the right format and with the right functions that the operating system needs in order to actually load and run your file. So if you notice when you write in C, you write a main function, but it's a function like any other function. And the naming of that is really just a convention. And as we'll see, the system needs to know about these conventions in order to be able to execute your main function. And that's also partly what the linker does. And then finally after all this process, we have a program. We have a program that can be run, in our case, on a GNU Linux system. And this is what you get in your hello program when you just have hello. The output of running GCC will give you this executable file. And finally, once we have that, this is where exec comes in. Exec contains the loader of the operating system, and the loader is what actually puts this into memory and branches to that main function ultimately and starts executing your program. Questions on the overview? So all these steps here are just taking your source code and turning it into some program that can actually be run on your hardware with your operating system. And it really does take all this in order to get a running program. Notice one little sort of anomaly here is that the linker is called LD, which is short for loader. But the linker is not the loader. This was, I don't remember the history behind this, but I think this is a misnomer. So the loader is not doing the loading into memory. It's the exec that's doing it. So the linker is just creating the executable file for you, and the loader is what's in the kernel that's actually running it. And also note here that on most operating systems like Linux, Unix variants, and Windows, the loader is implemented in the kernel code. This is in the part of the operating system that has privileged access to the hardware. So you, as in user space, assuming that the hardware protections are working correctly, you can't actually do the loading. You ask the kernel to do it on your path. This goes back to when we talked about the OS as an abstraction of the hardware. Okay, questions on this? Okay, let's take a look at, let's take a look at actually running this. And all these commands, they're in the notes from the lecture if you want to replicate these. Actually, I might as well just show them. So I'll come back to the diagram. All right, so here are the 5 steps that get us to a runnable, executable program. The loading part is when we call exec. So I'm just going to create a simple hello world program here. So here's my hello world program. Dirt simple, right? Notice I have this pound include. This is part of the preprocessor language. This isn't handled when you compile C. This is handled by a separate step called the preprocessor, which we can invoke using GCC-E. Let me do it. Oops. So GCC-E runs your preprocessor. Alternatively, you can do CPP, which confusingly does not stand for C++. It stands for C preprocessor. And you can use that to run the preprocessor step. So I'm going to take in my hello.c file. And by convention, the extension for a preprocessed C file is .i, perhaps for intermediate, I'm not sure. Okay, we've preprocessed our hello world program. Let's take a look now at what you get, what the C compiler actually sees when you run the preprocessor first. It is not a pretty sight. You get a huge amount of code, and all of this is just the contents of the standard IO.header file, .h file. Your code that you wrote is here. So we wrote literally 2 lines of code, and now we get 800 lines of code. And what's contained in here? Is this the implementation of printf, perhaps? No, it's not even the implementation. It's just a giant listing of function definitions. So here is hello.i, and you can see it contains a huge amount of function definitions. If we look inside of the header file, which is in user include standard.io.h, this is the C file that we're including with the include command. And what include does is it literally just cuts and pastes this code into your program. That's all, basically all the #include does. And so this giant, almost 1,000-line C program just gets pasted into your code. And you can see that it has a bunch of its own includes. And so this is including all of the definitions and macros and types that are defined by the C standard library. So even though you're writing one single line of code, because you're depending on the C standard library, you're importing a whole bunch of definitions for that C standard library. So you can see there's dozens of other #includes that also get included when you include standard IO. And if we look for printf, printf is just a declaration. So this does not even include the implementation of printf. This is just a declaration. You can see there's a semicolon here. There's no actual definition, implementation of the function. It's just the declaration. Okay, so that's pre-processing. Questions on this so far? Yeah.
Does adding all that code add to like space your program takes for the runtime?
Usually no, because these are all declarations. And as, well, we won't go into too much in detail about the way declarations work, but declarations are basically information to the compiler. They don't actually, they're not actually translated. Well, yeah, we'll see this when we do the compilation. Your declaration of symbols doesn't directly, what's that sound? Did somebody, somebody's not waking up right now because their alarm just went off on this phone, and they don't have it. So okay, yeah, these declarations don't get translated directly to machine code. So there's no machine code. I don't think their phone did that. I think I did that. And while the declarations, these header file declarations, don't contribute to the size of the binary, the implementations of them do. So that library code, that printf, and all of these standard IO functions you use do need to be accessible at runtime. So all this code was historically shipped. I'll talk about this when I get to the linker. But these days we have, there's more clever ways to give access to code at runtime, so you don't have to package this with your binary. But historically, yeah, and if you don't have support for what's called dynamic linking, you need to include all of this library code with your executable in order for it to run. And we'll see that when we get to linking, what that looks like. But good question, yeah. It doesn't, the header file, strictly speaking, does not add to your binary code. But it does, it's more code, so it needs to be processed by the compiler, but it's pretty fast to process. All right, other questions on pre-processing step? All right, so that's the preprocessor. So we took our C code, we preprocessed it, and now we get this nice big source file that's hundreds of lines long, when all we really wanted to do was just write one simple print statement. And now this is where compilation happens. So compilation will take this C code that we have here and translate it into assembly code. And we can run that with, let me get the, we can run this with GCC-S. So GCC-S runs compilation, including preprocessing, up to the assembly generation step. So let's take our intermediate file. This was our preprocessed C code, and write it out to, so -o is just out, the output file name, write it out to hello.s. Hello.s, this is our machine code, our assembly code. And this is what we get. So if you've ever done Intel assembly, this will look familiar. But even with learning, say, MIPS, which I think you learned in computer organization, some of these commands might look somewhat familiar. So you have memory loads, you have moves, which are a different type of, I forgot what they're called in MIPS. Add? Oh, add.
Yeah, there's no move in mix.
Oh, you just do add.
Add 0.
Oh, okay. Very reduced. So yeah, move is like add 0 in MIPS. We have function calls, which we'll talk about, and you'll have to actually implement. But you can see this is assembly code. This is the assembly code version of our C program. And notice that while this file is not small, it's almost 50 lines, most of this stuff, these dot operators, these are called pseudo ops. They're declaration stuff. They're not machine instructions. The number of the machine instructions here is very small. We have like 10 actual Intel assembly operations. And so you can see that we went from 800 lines into just like 10 assembly instructions, because these are declarations. These declarations are not actually machine code instructions. Okay, so there's our assembly. Questions about this? So we've gone from the C source, we preprocessed it, and now we've actually done the assembly step to produce assembly. And so this is the step that you'll be doing for your project. You'll be taking an input language and producing assembly code. It's simpler than C, but this is what you'll be doing. You'll actually be spitting out x86 assembly code. Yeah?
So where is the printf?
Oh, that's a good question. Where's the printf? Yeah, I forgot to mention this. So our compiler has translated this into put-s. This was either through the preprocessor. Well, actually, no, I don't think it was through the preprocessor because we still had printf. But the implementation of printf has used put-s. Put-s is a different library call which writes a string to the output. And I think this is because we didn't actually use any formatting stuff. Printf allows you to do formatting. You can print out like variables. So if we just print out a single string, somewhere along the line, this is being optimized to just use a different function, put-s, which does an equivalent thing. But yeah, good question. So this is the function call that's equivalent to to printf. Other questions on this? And you can also notice here that there's no arguments to call. Where are these arguments? Well, the arguments are being passed via registers. And this is one of the big difference between functions in the machine code level and functions at the programming language level. They don't behave the same way. And this is a lot of the work of writing the compiler, is actually simulating the behavior of the functions that we expect in machine code. And I'll talk about that a little today if we get to it, but we're definitely going to talk about it when we go to actually compile functions. All right, so that's assembly code. Now let's look at actually running the assembler. So the assembler, remember, takes machine code written in assembly and converts it to object code, converts it to the binary machine code. Oops. So let's take our assembler. So the assembler is a different program. This will also be run by GCC. GCC will also run the assembler for you. But here I'm going to take my input program, hello.s and write it out to hello.o. So .o, object file, is the kind of standard convention for object code, for machine code, that hasn't been linked yet. And now this is something that we can't view with a text editor because it's binary machine code. We can try, but it's not going to be, most of the stuff is not going to be ASCII characters that can be represented. But there's a tool called object dump that we can use to help us view this file. So it has a useful command called disassemble-d. So if you ever encounter, object code or machine code, you have a disassembler built in for you. This is, if you're interested in security or doing any reverse engineering, this is a kind of useful first tool to look at. And you can see it looks very much like our assembly code when we go to disassemble it. It has the same instructions roughly. There's some differences, like the name put s has been replaced with a number instead, with some offsets. And so the assembler is doing more than strictly one-to-one transformations. It also has its own kind of variables. There are assemblers that have macros and other sorts of language tools. But for basically, this is the same sequence of instructions that we got here from our assembly file. But remember, this is disassembled. So in the object file itself, strictly speaking, if we actually look at the hex dump of this, if we look at the hex dump of the .s assembly file, you can see it's ASCII text. Whereas we look at the object file, there's very few printable characters. We see the hello world characters in there because those are encoded in binary, which is just ASCII code that we can represent. But most of these are just non-printable ASCII characters because it's not ASCII. It's the binary machine code that represents the signals that actually go to the processor. Questions on this so far? Questions on this? So this is at the very top of our file. If you remember back to our files lectures, what is this? What's the first part of a binary file commonly? Yeah. Yeah, right, that's right, the magic bits. And so this tells us that this is an ELF file. I think it's executable linking format. This is the executable file format that's used by many Linux systems, and I think some Unix systems as well. So if you were to do this, say, on Windows and look at the binary file, you may have a different set of magic bits here. But this is, yeah.
You know that in all Windows programs, still today, there is a tiny docs program at the very beginning that just prints out this program cannot be run in docs mode.
That's very funny. I guess, yeah, Microsoft is very famously backwards compatible, I think. There's like 15 different open instructions or something.
So if you open any Windows executable, you'll see at the very top
the string
code, and then this program cannot be run in docs mode.
That's very funny. I was going to say unfortunately, but I don't have Windows here to test that. But by all means, test it yourself. Take a look yourself. Open it up in a text editor, and you should see that, what your colleague pointed out. Incidentally, there's a tool called Strings, which will just print out all of the ASCII printable text from any file. And this is all the ASCII text that's inside of our binary. Okay, so we've gotten through the compilation phase. What GCC will run for you, it'll run the preprocessor, it'll run the compiler, the assembler, turn things into object code. Okay, so now let's talk about linking. This object dump tool also has another flag, -t. This will print out the linking tables, the linker tables. So let me show you what this is. So this is a table of all the functions that are called and functions that are defined in your C code. So notice here that put s, which is our string printing function, it says here, UND. This stands for undefined. So in other words, the linker table reflects that we have a function call in our program, our print function, but no definition of it. And it also shows that we've got a function defined, main, where we do have a definition of it. It's actually defined in our file, and it gives you the location in the object file where that function is defined. So if we look again at our disassembled version of the program, we can't see it if, we'd have to look at the hex code, but if you look at the offset from the beginning of the file or the beginning of the segment, it'll show you where this main function lives. Actually, I think it's here. This is the offset, but it's, we don't have to worry about the actual offsets here, but the table will tell us whether a function is being defined or being used in our program. And this is what one of the things that the linker does. The linker resolves function calls with their actual definitions. And this is why you can write a program that calls printf or puts, but doesn't actually have to define it. So let me show a fuller example of this, which I hope will make this clearer. So let's make one program. I'm going to call it callee, that defines a function. Let's say it defines f, and it just returns 42. This is all it does. Not a very interesting function. And then let's define another function called caller. And inside of caller, I'm going to have our main method, and I'm going to call let's do it this way so we can see the function call. I'm going to call f and just print out its value. With me so far? Pretty straightforward program, right? Have you ever had to write programs in multiple C files before? Who's had to do this? Okay, not many. Okay, so you all write all your exercises in one file, right? Linux kernel is 20 million lines of code. Probably going to be inconvenient to do that and very slow to compile. But this is the norm. If you're doing any software engineering, it's the norm to have so-called separate compilation. And I think I briefly went over separate compilation a while ago. But all right, okay. So we've got our callee and our caller. These are probably bad names. These names are very similar. Let me change this to main. So we've got callee.c and main.c. So if you just run GCC with nothing else, let's say we just run GCC on main, or let's do it on callee. What's going to happen if I try to compile callee.c, this program? What do you think the compiler, if I just, with no other flags, I just call GCC, what's going to happen? It's going to complain. Why? What's it going to complain about? What's that? No, I'm compiling callee, this one. What's that? There's no main, yeah. So it's the same problem. And this is, if you look really closely, this is actually not a compiler error. This is an error in the LD program. What's the LD program? That's our linker. This is a linker error. So this program compiles just fine, and I'll prove it to you. I can use the -o flag, or actually maybe, so the -o flag will just do the compilation phases. Or sorry, the -c flag will just do the compilation phases. But let me, I'll just do the, I'll compile it to a .s file first. So let's take our callee.c and turn it into a .s file. And that's fine. It has no problem doing this for me. You can see I've got 42 in here. There's our 42. We'll talk about how that actually gets returned when we look at compilation. But here's our compiled callee function, our callee program. So this, when you do -c with GCC, it gives you these first part here. It doesn't run the linker. It just runs the compiler, including the preprocessor and assembly. So if I just use the -c flag here, I'm going to get our callee object file, and you can see here that it defines the f function, but there's no main function anywhere in this symbol table. But we compiled it, right? We compiled it successfully. There was no problem compiling it. It's just when we got to the linker was expecting main. And as one of your colleagues already pointed out, if we do the same thing for main.c, if we try to compile main.c, it won't actually complain the way you think. So it gives you warnings. And that's because I didn't have standard I/O. Remember, standard I/O just declares functions. It'll give you warnings that f is not declared, but it doesn't give you an error. The C compiler doesn't actually care if you have the functions declared yet. So let me just compile main.c to main.o and show you what its symbol table looks like, its linker table. And you can see here that we've got main defined, but we're missing printf and f. And so the compiler doesn't care about that. It's comfortable having undefined functions. It's the linker that will ensure that these functions eventually exist. And because of the code we're linking with, it expects main to be declared. That's why GCC gives you an error on callee.c, but it doesn't give you an error on main.c, because main is defined. Okay, with me so far on this? All right, so now we've got our two, let's get our callee, and let me compile but not link main.c. So here are our two programs. We've got callee.o, and this defines f, and we've got main.o. Let me bring them back up over here as well. So remember, callee.c defines f, main.c calls f. And here are what their linker tables look like after we compile them, but don't link them. We just compile them. So callee.o has the f function defined, and main.c or main.o knows that it calls f, but it's undefined. And incidentally, it also defines main. Okay, so this is where the linker comes in. Now, the commands to the linker, the stuff you have to link with in order for this to work with the loader, is way too complicated. I don't even know all the details of how this works, but basically there's a bunch of other code, these .o files, that implement the C runtime. And I'll talk about that briefly, but if we want this to run in our system, we need to link with all of this other code. Actually, I think I can link them together. Well, yeah, no, that won't work because we have hello in there, or we have printf in there. Let me take out the printf for a second to show you what this looks like. So we've got main.o calling f, but it's undefined, and we have callee.o defining f. So I should be able to link these into I should be able to link these together. I haven't actually tried this. So yeah, it's still, so it gave me a warning. So it allowed me to link these two programs together into something called main without .o. And if I dump the main symbol table, so this is after linking callee and main, you can see that f is defined and main is defined. Both are defined now because I've taken the object code from both of these C programs and I've combined them into a single binary. And what the linker does is it makes sure that function calls and function definitions match up, that we have the right addresses to call them. Because if you remember in MIPS, did you learn about function calls?
Yeah.
So function calls, they're basically just branches, they're go-tos. So what the linker does is just make sure that when you branch to that function, that we go to the right address. If we disassemble this linked file, you can see we have both f and main in the same program, and that we've got a call to the right address of f. Questions on this? This sort of makes sense? So we had two separate object files. One had an unknown function call, one defined that function. The linker will look at these two symbol tables and it will take the address of f in one object file, concatenate all of the assembly code, and make sure that the call to f in main, in the file that calls f, branches to the right address in this new combined object file. Make sense? Kind of make sense? All right, so that's what the linker does. And that's what the linker does for this simple program where we're not actually trying to run it. So once we try to run it, this is where the loader comes in. We need to make sure that we have support for the loader. And the loader in Linux-like operating systems don't call main. They call, by default, _start. So this is the default address to call in Linux-like loaders. So we had a warning here. The loader gave us a warning. It said cannot find entry symbol _start. And that's because in the Linux world, _start is the entry point. That is the place where the loader is going to branch to once you've loaded your executable into memory. And the loader is not going to have an error here because you can do whatever you want with the linker. But if you want it to be actually run by your OS, you need to have a symbol for start in your linker table. And so I've put links here if you're really curious about reverse engineering this. But basically, C has a default implementation for start, and it does things to help set up the main method. There are some initialization and some other stuff you can do with the main method, but basically it sets up your environment and your arguments for you. And this code is called the C runtime, and it's on your system at these locations. But basically what it means is that you have to also link these with your program if you want them to be executable as C programs. This also includes the dynamic linker, which does linking at program runtime. So this is a way to ease having to link statically all of the code into your binary. So dynamic linking is like super complicated. I've given you resources here if you want to learn more about how these work. But if you ever had DLL files on Windows, you ever seen DLL files? Those are the dynamic linker. And if you've ever been in DLL hell, where you have like the wrong versions of stuff, it can be painful, but it just reduces the size of the binary, and you can have everyone sharing the same linked code, and the code gets linked at runtime. But very much outside the scope of this class and my own knowledge of how they work. Yeah.
So like basically, whenever you're like running a program with printf, it's not going to have the implementation of printf in the program. It's going to be in a dynamic library loaded. So all of the
Exactly.
programs running on your computer are all sharing that same code.
Exactly. Yeah, that's right. So they're all sharing the same code. And you can even see this here where it says like put s at plt. This is part of the infrastructure that you're not actually calling the printf function. You're calling the dynamic loader, which will then go out and basically open the DLL file, load it into memory, do some rewriting of like function call tables, and then actually execute the function. So that way it only has to be loaded on demand. So if you don't actually call the function, it won't actually get loaded into memory. But once you load it into memory, it's loaded once, and you can keep calling it after that. The way this is implemented is like super complicated. If you want to take a look, if you're interested in like reverse engineering or security exploits, this might be good to look at. But I've left notes in the class notes to point to good articles that explain all this. So if you want to learn, especially the security implications of, I think it's the global offset table and some lookup table, how this stuff actually works, by all means, take a look at these. I didn't spend the time to actually. They're very complicated for me anyway. But anyway, you just have to know that there is dynamic linking that happens at runtime, and if we want our printf to work, and we want our C main to get called, we link with all of these other programs here. Okay, so here's going back to our hello object file. We had put s being undefined. Actually, I can probably do this with our callee. Let's do it with our callee. So here's callee.o and main.o. Let's see if we can use the dynamic linker, or use this C runtime, the dynamic linker, to make an executable main program. it didn't complain. So here's what our main program looks like now. Let's see, we've got main in here. So now main is defined. Main is defined for us. We've got where's F? We've got F defined because we linked together the program that defined main and the C program, that C source that can define F. And we also now have an implementation for the start, which is what the loader is expecting to branch to. And I've also left resources on the C runtime. You can see how it works, but effectively start will call main. I was playing with the disassembled version of this, and it's pretty complicated to see. So main is ultimately being called by start through another function that calls it. If you're curious, I can walk you through this a little bit, but it basically passes the address of main to that function, and then that function will call main for you. But so to summarize this, we had our two C files that were compiled into object code. One defined F, and one defined main but called F. After linking, we now have a program that both defines main, defines F, and calls F. We have a single program that does this, and by linking with the C runtime, which gives us integration with the C and the loader, we also have start defined, which is where our operating system is going to actually branch to start executing this program. All right, I know I went over a lot and I went off a little tangents, but questions on this process? So the linker took us from here, where we have two separate object files because we had two separate C programs, to this, where we have functions from both C files in the same program, as well as the machinery for the C runtime and loader. Yeah.
So the symbol tables here and the two above,
Yeah.
those are the same type of object, right? Those are object
Yeah, they're all ELF. They are the same type of file. Yeah, they're the same type of
With
file.
that in mind, why is there so much extra junk?
So this is part of the C runtime. So this is the part that helps call main. So not all of these are functions. The ones that are F. So some of these also have to do with other aspects of the system, like being able to relocate code in memory. I don't know what all of this. I don't know what all of this stuff is, to be honest. But there's stuff here related to the dynamic linker, to the C runtime, and for the loader. So, but not all these are functions. So some of these are also other information. So this is related to the dynamic linker stuff here. But in terms of functions, there's only the main function. And so F is a function, the main function, the entry point for the loader. I don't know what this does. This is related to, program. I think it's this has to do with being able to relocate code in memory at runtime. This is F that we defined. And this is the dynamic part of this is what's going to be loaded by the dynamic loader, the dynamic part of the C runtime. But that's all the functions that are in here. The rest is not function calls. But if you're interested in what all of this means, take a look at the notes that I have in here, so you can see more details about ELF, how the actual programs get run, and about dynamic linking and loading, and the C runtime. So they're very nitty-gritty nuts and bolts of OS. I would say take an OS course, but I'm not sure they're even going to cover this in an OS course. But each of these has a specific problem they're solving. So dynamic linking solves the problem of having giant binaries and everybody linking the same code. Program-independent code allows your program to be moved around in memory without having to have fixed addresses. And then linking, of course, just makes it so you can have separate compilation. You can have multiple C files that are compiled separately that define the functions that your main program calls. Okay, that was a lot. I know that was a lot. But now finally we're at the loading step. And you actually wrote this in your, or may have if you finished the project. Now we're at the loading phase. Now that we have our executable code, we have all our functions available, we have the C runtime available, we've defined the start entry point, which is what the loader expects by default. Now we can actually run the program. And if you've done the process, if you looked at the lectures on shells and processes, and you've written your shell script, what system call gets called when I do this, when I run a program? Yeah. Yeah, go ahead. Exec. Yeah, exec gets called. Exec contains the loader. So it like doesn't even say it, but it says load in here. But this is what actually takes your executable file in its format. And they might even mention start in here. Okay, I think it's a system default, probably not to find there. But exec is what actually runs the loader. And so finally, when we call main, there's nothing to see. It doesn't actually do anything. But if we call hello, which calls printf, we can see. Oops. We can see hello getting run. And so voila, we've got a runnable program. All right, so just to review briefly, to give us this executable program, in C we had first preprocessed, which included headers and does other things like macros and conditional compilation. Then we took this, what is now pure C, we turned it into assembly. This was the compilation step. That's what we're going to do in our project. The assembler took assembly code and made it into object code, which is the actual binary machine code. And the linker allowed us to have separate compilation and also linked with the C runtime and other facilities that we need to load the program. And then finally, the loader takes this executable binary format, and the operating system or the kernel will actually put your code in memory and branch to the start label so that your machine, your physical machine, is actually now running this program. All right, questions on this? Thoughts? So at a high level, at least, is this somewhat clear, I hope. Now take a look. You can take a look yourself and actually run. You can run these steps on Eustace or your own machine if you have a Linux machine somewhere, or WS, a Windows subsystem for Linux. And you can see this, and I've even given examples here where you print out each of the steps so you can see what each of the steps looks like. All right, other questions on this? Yeah.
Out of curiosity, in the kind of loaded file we were showing a little earlier, there was a blank line for like an address. You know how it was just main.c and stuff? There was just a blank line. Yeah.
Was it in this program?
Under main.c.
Let's see. Yeah, I have no idea. I have no idea what that is. It's all at address 0. So I don't know. Yeah, no clue. I don't know why there's a blank line. Don't know what it means. Sorry. Yeah, I don't know. Maybe it's just some text there or something. It's a blank text. Don't know. Okay, other questions on how source code becomes a running program? Source code becomes a process? Yeah.
You said that for the speed preprocessor,
Yeah.
has that line and stuff like that. That's a different way.
Yeah. Yeah, basically it is. So let's see. We have a little more time left. So, all right, the ABI is a little more involved. We'll get to that when we get to function calls. Let me show you, especially since there was a question about the preprocessor. Let me show you a little more about what the preprocessor does and what it looks like. Okay, so recall back that we had this main function that called f in main.c, and we had callee.c, which defined f. If we just try to compile this into a single program, so if you run GCC by default, it'll do all of those steps for you. It'll do the preprocessing, compilation, assembling, and linking. It'll do all that for you. So I'm just gonna recompile this program with a single GCC command. So this is This is what it looks like, gcc-o main, call-e.c, main.c. Everybody good on this? This is just how you call GCC with multiple C programs. Notice I got this warning here. So it said implicit declaration of function f. So in C, you're supposed to declare functions before you define them. Now, we could, but this function is being defined in call-e.c. It's being defined in a different program. So how can we resolve this? So one thing we can do is, let's say f takes, 2 integers. And just does some computation on them. Now, when the compiler compiles main.c, remember, it's compiling it by itself, so it doesn't have this information from call-e.c. But in C, how do you declare a function? Well, you can declare it like this, right? You can just put a function declaration without its definition. And if maybe you are in CS1, and you're like, well, I kept getting this compiler warning. So if I just put this declaration, or you've defined the function after another function and it complains to you. So my warning goes away, so now it's defined. But these seem kind of disconnected, right? Like I've duplicately declared f in this file and in this file. So this is what header files are used to resolve. So instead of having to copy every declaration of every function that I'm going to use in every program I want to use it, I can instead create a header file, and by convention, I'll call it call-e.h. It'll be the header file associated with this code, so like standard.io.h. And I'm going to put my function declaration in here instead, inside of call-e.h. And to avoid having to copy that code in every program that I want to use it, this is where include comes in. So now in every program that might use f, I could put it here, although it's kind of unnecessary, but every program that I want to use f in, like let's say I have another program called call-f, now every program that I use f in, all I have to do is just include this call-e.h. And that's that's one way people use the preprocessor, and that's what those header files are doing. So that's why when we saw standard.io.h, it was just a bunch of declarations. It didn't actually contain the implementation of printf. It was just declarations so that the compiler will know where to find or what that declaration of that function is. So it can just check that you're calling it correctly and give you any warnings. So if I called f incorrectly in my call-f program, then my compiler will just warn me, or actually give an error. It'll reject this program because I haven't called f correctly. So that's what those type declarations do. They're just information to the compiler to help it check whether you've used functions or other symbols correctly. Okay, let me show you a few other kind of sillier preprocessor tricks in the time. Well, so first of all, any other questions on this? Yeah.
So how does the compiler know that when you're doing calling.h and you're calling that? How does it know that? Because you only have the implementation in calling.h.
Oh, okay, so this comes back. Okay, good question. So, all right, so we've got, let me put this, maybe move past this too quickly. So here's my call-e.c. This is my implementation. Here's my call-e.h. This is my declaration. And here's the user of f, main.c, which includes call-e.h to have the declaration of the function. And then now the compiler can just check that you're calling f correctly. So this is my setup. Now the question was, how does main.c know about the implementation of call-e.c, right? So remember that when we go to compile these, if I do -C for compile, and I go to compile main.c, what do I get? I get a binary file that doesn't have the implementation of f. So the compiler will happily compile this program because it doesn't actually need, so what it does is it compiles each function, and it doesn't need to know, it just assumes that the implementation of all functions called there will be available at runtime. But in order to compile it, we don't actually have to know what the implementation is. We can just call that function. We can generate code, and we'll see this when we generate code, but we'll just generate code that calls f. But where f is irrelevant to the compiler at this point. When it matters is when we're actually running the program, when we actually have our complete program. So even though we've got generated assembly code that calls f, so this is our assembly code, it calls, well, 1b is going to correspond to f at runtime. Remember, our linker table is missing it. So what makes this f available to our main method? That's the linker. So if you remember, we compiled main and callee separately, and each has its own separate symbol table. The main object code calls f, but it doesn't have an implementation of f in that file. This callee.o does have an implementation. So when we call the linker on this, the linker will resolve the location of f and the call of f. So that's what we did with the linker. So now this combined program has f defined and main defined in the same program. So to answer your question, it's the linker that does that. It's the linker that ensures your final program has access to all the functions that are being called. And that's why if we just try to compile main.o by itself, that's why we get a linker error, because the linker will catch that we've got functions being called that haven't been defined anywhere. And so it won't even let you produce the final program. The linker will require that all calls are resolved to some address, some jump that it's going to jump to at runtime, or it has to resolve to some address in the same binary. So yeah, this shows how the interaction between the preprocessor and the compiler and the linker work together to allow separate compilation, to allow you to have library calls like printf, things that you don't have to write yourself. So this is like the kind of low-level Unix-like C system way of doing this, but all programming languages have some sort of feature like this. At least all kind of widely used ones, like Java. C++ works the same way, more or less. Java, even Python, interpreted languages, they all have facilities for having separate definitions of code, libraries code. But yeah, good question. And so this is the preprocessor side. This is how the compiler will be able to know about the definition of this function, really purely for doing checking. So you could kind of subvert these checks. You could get past these checks and just have it call, so C will, if it sees an undefined function, it'll still compile it. But if you don't know the types and number of the parameters, at runtime you may get bad things happening. You may get unexpected stuff happening. All right, other questions on this? Yeah. 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 You want to take a look at this? Oh yeah, good idea. So here's what main.c looks like after pre-processing. So these hash mark lines, you can think of these like comments. You can ignore these. They're not actually comments, but you can think of them like that. So here's the program we wrote, and here is what include gets expanded to. Notice we have the exact code from callee.h literally just copied into our pre-processed C file. So yeah, that's another good question to see. So this is what the pre-processed version looks like. And so really it's just cutting and pasting code. What that means is also it doesn't really matter what code goes in here. So I could let's see. I could put a function definition in here if I wanted. You can put a function definition in here. Let's see if I have time to show this. So I could put a function definition in here, and voila, it's here in the code. I could even put a definition of f in here. So here's a definition of f. It always returns 5. And now when I go to compile main.c, I won't get a linker error anymore because I have a definition of f here. Because I've defined it in my header file. So there's the definition. But what do you think will happen if I try to combine this with call e.c? So I try to compile both this program that defines f and I compile this program that also defines f. What's going to happen with the linker? The linker now has 2 object files. They both have a definition of f. What's going to happen? What's that? Error. Yeah, it'll be whoops. Error. So sure, it could like pick one. You could resolve this in any way, but the linker will check that you also check that you don't have multiple definitions of the same f. And so here it is. Here's the linker error, complaining that you've got multiple definitions of f. So this is why you could put definitions in H, and actually in C++ with templates, for those few of you who do C++, it is common to put implementations in header files because you need especially for templates. But just by convention, implementations are put in .c files and declarations are put in .h files by convention. But it's not strictly enforced because the .8 they include will literally just copy the stuff into the .h file. So let me just show you one kind of silly trick if you ever wanted to, impress people at a party. So this is, let's do it this way. Will this program compile? This program has no problem compiling. Why? I just took away the curly brace. Well, another feature of the preprocessor is macros, and you can cause all sorts of mayhem with macros because they're basically code generators. Even real-world systems will use macros to generate like entire functions, and you can do all sorts of crazy stuff with macros. And this is one of the funny things that you can do if you want to change it. Yeah.
Make it colon, make it like Python.
Oh, like this. So, okay. So it's restricted to C identifiers, unfortunately. So you can't take any token here. This must be a C identifier. But I could make it like another language, like that. But it's restricted to C identifiers. All right, so that's 1020. There's a little silly trick. Look at the C obfuscation contest if you want to see more craziness from C. But otherwise, have a good one.